So my name is Klaus Iglberger. I'm working at Elektrobit, which you might not know, but in fact, Elektrobit is one of the largest manufacturers or software houses for automotive software. So I'm working in the field of navigation systems. I think that's enough. So I am astounded by the number of people in this room. So when I submitted the talk, I would not have expected that so many people are interested in this topic. So I was hoping for this presentation to be accepted, was not expecting this to be one of the popular talks. However, I have to admit I'm a little bit worried. I'm a little bit worried because I expect that the majority of you are here because you're expecting a talk about template metaprogramming, some fancy, in-depth C++. So be honest, who is expecting a talk about template metaprogramming? So I kind of expected that. So unfortunately, bad news first, this is not going to be a talk about template metaprogramming. But stay seated. The message that I have is probably much, much more important. And the message that I have is, in fact, inspired by a slide that we saw last year at Meeting C++ 2013, a slide from the talk by Eric Niebler, so the keynote that he gave us. And what he told us is, we need libraries, desperately libraries for C++ 17. Please contribute libraries. And what caught my attention was that he's looking for linear algebra libraries, so not he, but the committee. Apparently they want a linear algebra library, but also apparently they have not found one yet, so there's the sad face still. So keep this slide in the back of your mind throughout the presentation. We'll come back to this by the end, and we'll kind of discuss this sad face a little bit. So what I want to do is, I want to, as the title suggests, revisit expression templates. I want to reevaluate them based on some common statements that you find across literature. So papers, books, etc. And these are the 6 statements that I found. First one, expression templates are easy to use and apply. Statement number 2, expression templates are easy to maintain. Statement number 3, expression templates are a performance optimization. Statement number 4, expression templates help the compiler to produce optimized code. Statement number 5, expression templates are easily parallelized. And last but not least, expression templates are obsolete due to C++11 move semantics. Okay, so from these statements alone, you get an impression, okay, it's obviously about efficiency, mainly. Yeah, so performance, optimized code, parallel code. So where does this come from? So let's spend a couple of minutes to see where it all started. So in fact, it started in 1995 in the C++ report with a paper by Todd Feldhuisen called Expression Templates. In this paper, he explained the general idea of expression templates, and he gave a couple of summaries. The first, it evaluates vector expressions at 95 to 99.5% efficiency of hand-coded C. So this is, I think, even in the abstract of this paper. And also, the speed is 2 to 15 times that of a conventional C++ vector class. That's amazing. 2 to 15 times the performance. This is definitely a win. And this is why this idea caught on so quickly. This is why, for instance, this book, that I assume all of you know already, covers this topic in a separate chapter. And they say, expression templates were originally developed to support high-performance array operations. So again, the notion of high performance. Also, expression templates are very effective for operations on medium to large array sized at runtime. So you get a feeling there is a common attitude. And this is exactly what I want to reevaluate. I kind of assume everybody here is familiar with expression templates. Still, I think it is important to recap the most important details, because this is what we'll build on. So the first thing is we will only deal with linear algebra, because this is kind of the original the origin of expression templates. This should be perfectly enough for our purposes. Someone mentioned I should talk about proto. This is not about proto. It is exactly just about these statements that I showed you. So, a quick recap. This is kind of the classical examples that you see. You have three vectors, A, B, and C, and you want to compute the vector addition. The classical way to implement this is by overloading the addition operator. You pass vector A and vector B as references. However, this is exactly the problem. You have to create a temporary vector inside this function. The vector is sized accordingly. You have a for loop that traverses the elements of A and B. Now, assuming that they have the same size, of course. You compute the sum of these two vectors, store it in this temporary, and afterwards return the temporary vector. And that is, of course, a problem. We have to allocate memory. We have to do a copy operation, which might be pretty expensive depending on the size of this vector. And of course, there's also deallocation involved. So at least three operations that we can completely get rid of. Because what we actually want to do is just a plain for loop computing the sum of the elements. So doing an element-wise addition of A and B and store the result directly into C. It's the most simple thing we can do, the most efficient thing that we can do. Right? So the idea of expression templates is such, don't compute the resulting vector immediately. Instead, replace the result by some kind of proxy object. This proxy replaces the result, represents the result. It essentially just has to store the two operands. So A and B, so the left-hand side and right-hand side operand. It provides an operator that you can access the individual elements. Yeah, so inside this operator, we do some addition. It has, of course, also size, so this kind of represents a vector on its own. And of course, I store everything by reference, so there's no copy involved. Then the addition operator is simplified to just simply return an object of this kind. So the addition yields a sum object. I can use the sum to compute the addition of two vectors. And this is then used in, for instance, the assignment operator of such a vector class. In this assignment operator, we first resize accordingly, and we traverse this right-hand side expression, we assign the values, that's it. Okay, I think this is what you know. However, let me point out again, this is the one for loop in the system. So we saw in the C code example, there's one for loop doing the addition. Now this here is this one for loop. The next line is where the magic happens. This evaluates the right-hand side expression regardless of what it is. Might be an addition, might be a subtraction, kind of multiplication. This is where all things get evaluated. Not any earlier, so this is true lazy evaluation. Okay? I think this is kind of what you know, but I think it is important to get reminded of the core of what expression templates offers. So now let's get started re-evaluating them, just based on what we just saw on this very simple code. So these are the statements that are also printed in the abstract. Therefore, I have to cover them. But fact is, I think the first two are kind of dull in comparison to the other ones. So let's cover the first two a little quicker and then concentrate on the really interesting part. So expression templates are easy to use and apply. So I think this is kind of something that we can fully agree on. If you see this code, if you can truly add two vectors by just using the addition operator, this is as intuitive as it's going to be. This is as maintainable as it's going to be. So of course, they are easy to use and apply. That's the point of expression templates, to kind of represent a domain-specific language. So yes, I think this is truly a correct statement. Okay, expression templates are easy to maintain. Well, I already said it essentially. If this is what we use, then the user of the library, of course, has a huge advantage. If this is all he has to do, then of course his code is easy to maintain. So at this point, I would say easy to maintain. However, there's of course the other side of maintaining the expression template library itself. Now this would definitively involve a lot of discussion. Is this easy? Is it not easy? So if you've seen a full-blown expression template library, I think you might agree it's not so maintainable. So heavily templated, very contrived, well, not so much. So this is side easy to use, but for the maintainer of the expression template library, probably not so much. Okay. Expression templates are performance optimization. This is essentially what we learned from all the publications out there. So let's take, again, the classical examples of adding two vectors and take a closer look at it. So I picked two libraries, two classical libraries that are implemented using expression templates. The first one is the classical library, the one that Todd Veldhuisen implemented himself, the Blitz++ library, now even in version 0.10. So I think the last one Todd contributed to was 0.9, so I used the newest one, of course. The second one is the Boost uPlus library. So also Boost has a expression template based linear algebra library called uPlus. I used the version from 1.54. Okay. In order to make sure that everything compiles cleanly, that we truly get the maximum performance, I first take care of truly using the machine, yeah, to its maximum. So AVX, so this is an AVX machine that I'm using. So I make sure that the compiler knows, okay, I may use AVX instructions. Second, maximum efficiency level, no debug mode, of course, and a lot of additional compiler flags to make sure inlining truly works. This is probably one of the major disadvantages of expression templates. Everything needs to be inline to truly get to this, back to the C code. So, looks a little scary, but I truly made sure everything runs at maximum performance. So, this is exactly what you get if you just benchmark these two libraries across a vector ranging from one single element to 10 million elements. And this is the curve that you would expect, kind of. So what we see is that initially performance grows because this is a logarithmic scale, so performance maxes out somewhere here, vector size of 200. This is where the level 1 cache then is saturated. So everything fits into the level 1 cache. At some point, the vectors are too big. You fall back into the level 2 cache. Now, this machine even has a third level cache. This is what you see here. And if the data even grows larger, then at some point, you're in the main memory. So obviously, the main memory is much, much slower than the level 1 cache. This is to be expected. So level 1 is truly fast. It's probably the fastest that you can, it is the fastest you can get. A couple of nanoseconds delay. This here is about 200 times slower than level 1. So if you truly have to work with the main memory, this is really, really slow in comparison. So however, for this operation, it's perfectly okay. There is not much to compute. So essentially, we spent the entire time waiting for data. And if we get some data, we do one addition, and then we wait for data again. So this is why at some point, the performance is simply down here. OK. What about classic C++ now? So of course, we would expect it to be considerably lower to this graph, and this is exactly what happens. So if you implement a naive classic addition operator, this is the performance that we get. And you see there is truly a considerable overhead involved with this allocation, copy operation, and deallocation. Especially here, this is where you get an enormous factor, but also here in the end, there's at least a factor of 2. So yes, of course. Expression templates give us a shot. And a third benchmark is just to benchmark C code, plain C code. And yes, you see, we have exactly the same performance as these expression templates. So apparently, they truly improve our performance. They truly are a performance optimization. So at this point, yes. And this is exactly what you read in, well, basically all papers that you see. please. So I'll come to the discussion later on. Yeah. So this is where usually this discussion stops, right? Unfortunately. But in this presentation, let's dig a little deeper. The vector addition is a so-called Blas level 1 operation. Blas level 1 means it scales linearly with a number of elements. Blas level 2 means something like a matrix vector multiplication. And at the other end is Blas level 3, which is matrix multiplication, for instance. So let's take a look at the matrix multiplication. So 3 matrices, A times B, the result is assigned to C. This is the result we get from U plus and Blitz plus plus. Looks about reasonable, right? So about the same shape as the vector addition. So yeah, we don't think much about it. So however, you might have heard about matrix multiplication. So when do companies like Intel or AMD use a matrix multiplication? They use it primarily to show off their CPUs, because matrix multiplication is one of the rare algorithms that can truly heat up a CPU to the maximum performance. Yeah? So first, we of course have to think about what is the maximum performance of this particular CPU. So it's an Ivy Bridge CPU at 2.2 gigahertz, which I kept constant, so it is fixed. It's not, the speed step is disabled. This is what peak performance is up here. Yeah? And it's easily computed. So 2.2 gigahertz times 8. So this 8 is a multiplication of 2 because it does multiplication and addition at the same time. And additionally, we use AVX. AVX is able to compute 4 operations in one operation. So at least if we use double precision, this is what we're doing here. So 17,600 megaflops is the maximum. And there's, of course, a gap. And unfortunately, this gap is something that you also see if they compete against the library that is truly optimized. So the MKL is Intel's product. They hire a couple of engineers just to optimize operations, so like matrix multiplication for their CPUs. OK. Apparently, Boost and U+ do not perform too well in this competition. OK, of course, U+ does not hire people to just optimize matrix multiplication. Would be surprising. At least we gain a little of performance in comparison to classical C++, right? Because of this copy operation, memory allocation, etc. So, unfortunately not. So, apparently, even classic C++, so including copy operations, etc., is faster than what the expression template libraries provide us. Hopefully, this is kind of surprising at this point, because we started off with the attitude that we actually gain performance. Now we are losing performance in one of the most important benchmarks that exists. So matrix multiplication is truly important. So how do we explain to people, well, this is important, but OK, we are down here. It's not so bad after all. Of course, this is truly bad. Truly, truly bad. This is a disaster. OK. What happens? This is what comes out if all the inlining stuff works properly, etc. This is what the compiler should uncover. 3 for loops. The inner 2 loops. So, OK, other way. The outer 2 loops, I and j, are for the result value. So essentially, you see that we compute a single value of C, of the final matrix C, before going to the next one. Yeah? So if you visualize this, imagine that these are 3 matrices that I want to multiply. This is what I use essentially. I multiply this row by this column, assign the final result to C. Of course, I use this value here to sum up everything, but OK. And then I go to the next value, use this row, and the next column, etc. So this is kind of the normal multiplication, matrix multiplication that we see, or that we know from mathematics. The problem here is, of course, the data. This is in no way cache-aware or data-driven. We just use the data randomly. Imagine that this is not just a 5 by 5 matrix, but that this is truly a large matrix. Then the first thing you do is we load the first cache line. We only use a single value of this cache line. So 8 byte from probably 64 bytes. So 1/8 of the cache line is used. Okay, then we load another cache line using a single value, and so on, until the cache is full. Then, if the matrices are truly large, I load the next value, and the first one is evicted from cache. So I've not used anything but a single value from this one cache line. And this is why the performance is so devastating. I don't really use the data I've waited for so long. So 200 times as long as I would have used the level 1 cache. Of course, some might argue it could get worse. We could also use this matrix in a bad fashion. So if this would be column major, then of course it would be even worse. But yeah, it is bad enough. I have to admit, I tweaked the classic code a little bit. If I use exactly the same algorithm, of course, it would run slower. However, this tweaking is so simple that it's actually not a real effort. I just changed 2 loops. So now the result is not from the 2 outer loops, so I, J, K, but now it's I and K, not I and J. So essentially, if I again visualize that, what I'm doing is simultaneously I compute the result of entire row. Yeah? And by that, I have some cache reuse. Of course, for every row, I have to load the entire matrix B. So I load it several times in the course of the entire matrix multiplication. But I reuse the values that I load. And this is why this copy operation, this memory allocation, are not interesting anymore at all. I gain a huge performance by just using the cache lines efficiently. Okay. I would say at this point, clearly, expression templates are not a performance optimization. Definitively not. They are far from being a performance optimization. Expression templates are, in fact, an abstraction technique. You're abstracting the fact that you have something on the right-hand side. So you don't care if it's an addition, a subtraction, a multiplication. You just use the right-hand side operand as if it would be something that could be easily used. But unfortunately, it isn't. So it is abstraction. And abstraction is the opposite of optimizing. Because for performance optimization, you need the details. You truly want to exploit all information available. And so data hiding, so hiding the data and operation types. And operation types means addition, subtraction, multiplication, etc. And the single element access is simply insufficient. It doesn't work. You cannot expect this to give you magically some performance. Yeah? So in 2012, I had some time left, so I was still at university by this time. So I wrote a paper about this, also called Expression Templates Revisited, where we actually investigated this phenomenon in detail. So in this paper, you'll find some tables taking a look at instructions, loads, etc. So very detailed. The results are kind of devastating for the attitude of expression templates be performance optimization. There is very little ground for the reputation of expression templates to be a performance optimization for array operations. We have shown that the widespread belief in advanced inlining and optimization capabilities of C++ compilers is naive and unjustified. So essentially, the entire belief that the compiler is fixing this for us, is assembling us the code that runs fastest, is simply not working. Also, in this paper, we introduced some notion of smart expression templates. So, okay, the term might not be so relevant here. The idea is kind of simple. Smart expression templates, first of all, don't expect the compiler to do anything, except perhaps inlining. Inlining is still a problem. But we do not expect the compiler to provide us with some magical performance. Doesn't work, will not happen. Instead, we use truly manually optimized kernels. And in a full-blown math library, this is about 100 kernels that you have to manually optimize. This is a lot of work. This is also a lot of frustrating work because on one machine it's working like this, on the other it's not working, so you have to make sure that it's working over on all platforms. So this is essentially what Intel is doing in these BLAS libraries, so like the MKL. And also, smart expressions mainly exploit lazy evaluation. This is kind of the key feature, which I'm going to show you. Okay, just to show you it's actually working if you're doing it right. If you do not rely on a compiler, these are 3 libraries that, to a larger or lesser extent, implement this idea of smart expression templates. There's the MTL, so Peter Gottschling might be in this room, is one of the main contributors here. The eigen3 library is pretty well known, and there is a library called Blaze. So I used not the newest library, so the benchmark results are a couple of months old, but still the result is comparable. And this is what you get for matrix-matrix multiplication. The orange line is the MKL. This is what we want to have. And you see that all those smart expression template libraries, the MTL, Blaze, also Eigen, I'll explain shortly, have about the performance that we expect. So Eigen is a little special in the sense that Eigen unfortunately doesn't use AVX yet, but only SSE. And SSE meaning just 128 instead of 256-bit registers, yeah, wastes about 50% of the maximum performance. But still, they achieve this 50%, so it is still a remarkable result. So if you're doing it correctly, apparently you truly uncovered the result of, or come to the result of the MKL. For instance, what you could do, of course, this is what Blaze and the MTL do for, at some point, you can switch internally to the MKL or any other BLAS implementation. So you don't have to implement all the kernels yourself. Of course, you can use something that's already on the market, freely available. So and if you cannot afford the MKL, use Atlas. Atlas is for free. So you just have to use these libraries accordingly. So the idea has kind of caught on. So apparently the Boost developers realized, oh my, we're doing something pretty stupid here. And so there was an initiative in the Summer of Code this year that suggested to optimize the Boost UPLAS using some smart templating. So I still say it's smart expression templates, so that the term sticks. So also they provided some sample of their code. However, I'm very, well, I don't expect this to work as you would expect. You cannot suddenly turn an architecture that is fully expecting the compiler to do everything to something that is uncovering full performance for every operation. Unfortunately, you basically have to start from scratch. So I haven't taken a look at it yet. I didn't have the time, but don't expect too much in this case. Okay. This is a clear negative point. Expression templates simply have nothing to do with performance optimization. Okay. Well, however, at least expression templates could help the compiler to produce some optimized code, right? So let's go back to the vector addition. This is where we left off. The graph that you saw last, we see that UPLAS and Blitz++ have about the same performance as C code, and the classic one sucks in this particular benchmark. We did not think of the maximum performance that this operation can achieve. So if we think about this, we realize, oh, there's also some gap. The theoretical peak performance of this operation is up here, which is considerably lower than the matrix multiplication, simply because we're only doing additions in this case, and also there are some limitations in the store and load operations. So you cannot do everything at once. So this is the maximum one that you can get. 2.2 gigahertz times 2, so 4,400 megaflops. This is what the performance that we truly want to see. Yeah? And using some of these libraries, you truly get the performance that you would expect. So in this particular benchmark, Blaze seems to be the only library that truly achieves maximum performance. Not because they rely on the compiler, but because they have handcrafted kernels just specifically focusing on this particular problem. Small-sized vectors, so in cache, whatever is necessary. You notice that in the end, everything has the same performance. So for the truly interesting problems, it apparently, in this case, doesn't matter. So the vector addition in comparison to the matrix multiplication is a bandwidth-limited operation. With a single thread, we cannot go beyond this limit, so all the libraries will have this maximum performance regardless of how they're implemented. Okay. Generally speaking, I believe that as C++ developers, we unfortunately tend to first believe too much in the compiler, believe way too much that the compiler will fix things for us, that all those optimizations are possible. Very often, unfortunately, this is not possible for many reasons. So you might believe that the C code that I showed before, the C for loop, is something that a compiler can optimize. Apparently not. So with all these optimizations activated, still the C code does not run at peak performance. Interestingly, because this is kind of the simplest operation that you can throw at a compiler, vector addition. Unfortunately, also, we kind of omit profiling. We do not think about what performance do we expect. We simply believe it's fast. Yeah? We omit profiling and still, well, say, OK, I'm fast, because the compiler will take care of this. This, unfortunately, this kind of attitude can have truly dramatic effects. So let me tell you one story involving this particular machine that I was working on a couple of years ago. So some of you might know this. This is at the Compute Center in Munich, the Edge LRB2 machine, now not used any longer because they have a newer one, much faster one. So let's call the person I'm talking about John. So John wanted to run a particular simulation on this machine. So John ran the code, and then in order to get some runtime on the machine, you have to ask, may I run my code on the machine? You have to be given some time on the machine. So, and these assessors were confused because John's code only got about 5% of the peak performance of the machine. 5% is not so much. So they asked him, why is it only 5%? And John said, well, it's probably 5% because it's the maximum. Because I'm using expression templates, my code is fast. So they insisted there must be something wrong. Apparently, it is probably because of your expression templates. No, my expression templates are definitively improving my performance. So end of story. John was forced to remove all expression templates. Otherwise, he would not have got any further funding. And suddenly, magically, the code was about twice or thrice faster, so 15 to 20% peak performance, which is not bad. So it depends on the algorithm. So end of the story is that a couple of people who are truly worried about performance now, again, believe C++ is a slow programming language. People just don't know how to get to true performance when using C++. Even people who run on these machines, and these are truly expensive. Whew, that's bad. But, well, are the guys right in the first place? Can you simply say, don't use expression templates, or may they forbid someone to use this? Well, in order to understand these guys, we have to think about two things. So usually, in the code that you're writing, the majority of costs is produced by maintenance. So 60% on average about the costs that we have is maintenance. Yeah, the rest, the 40% is for development. On average, so depending on projects, long-term, short-term, etc. If we drive down our maintenance costs, we gain money, or we save money. That's a good thing. In this HPC, high-performance computing business, it's unfortunately a completely different story. 50% of the cost is hardware. These machines cost millions. Yeah, several millions. So I think this was even a cheap one. So now we are going above 10 millions, etc. 25% of just for energy to run these compute centers. And a mere 12% now is staff. Okay, and 13% is just rest. So in order to save money, what you have to do is to improve your performance such that the hardware is used as efficiently as possible. If you can truly tweak about 5% of performance of about 10 projects. So this is what this paper shows, very, very illuminating. If you just improve the performance a little bit, you already save kind of millions of euros. And of course, you can use this money to hire more staff, which then again improves the performance, which again saves money. You can hire more people. And so for them, performance is truly important. It's their #1 metric, and for good reasons. So in general, unfortunately, I always get the feeling that C++ has a very bad image in terms of performance, a very bad image, because we are yet not using it such as it should be used. And it's even considered slow in some communities. And now back to your discussion. So Fortran is still considered the programming language if it's about performance, because Fortran doesn't allow you too much freedom. So Fortran is completely focused on data-driven development. However, you saw the result from this slide here, matrix multiplication. And you see that, so the MKL is probably a Fortran library, probably the low-level kernels on Fortran. What is in C or C++ is the interface. Eventually, you call some Fortran kernel. But you see, this library here is C++ only. And apparently, for small matrices, it even outperforms the MKL for several reasons. So the Fortran kernels are function calls. It's probably not a single function call, it's probably multiple function calls. So the first one is a very general one. Then depending on these 14 arguments, you're calling different kernels, more specialized kernels that are truly focused on a particular problem. So a lot of function calls, nothing is inlined, so of course it starts off pretty slowly. C++ code can, at compile time, depending on the given data, decide which kernel is best. Run the according kernels that are suited for smaller matrices. So in C++, we have a lot that we can use to actually make code faster. We just have to use it properly. This is actually why this library here goes until a certain point faster than the MKL, which is still moderately sized matrices, again, logarithmic scaling. And at some point, it simply switches to use the MKL, because this is just one of the fastest implementations that you can get for large matrices. So this year at CPPCon 2014, Chandler Carew told you exactly this thing. And I think this is, to the point, one of the best quotes that I can offer. C++ doesn't give you performance. It gives you control over performance. But you have still to make the best out of it. You cannot believe that the compiler will magically turn everything into fast code. It doesn't work like this, unfortunately. So, do expression templates help? No, not at all, not a bit. You have to be you are in control. You have to make sure it's working on your own. Okay. Expression templates are easily parallelized. I think this one is pretty important, very important. If you go to a store today, what can you buy? You cannot buy a single-core CPU anymore. There is no such thing as a single-core CPU anymore, kind of. There is, but the current CPUs are multi-core. That's just the truth that we have to live with. Yeah. So you have multiple cores of the same kind usually. You have a lot of cache, of course, but this is the kind of CPU that we have to work with. 2004, that's the important number here. In 2004, Herb Sutter already announced that the free lunch is over. And what he was talking about is we cannot think single-threaded anymore. We have to truly work in a multi-threaded world. This is just reality, if you care about performance. So, one suggestion in some papers is, well, expression templates are easily parallelized because I just have this one for loop. And one for loop can be easily parallelized by just putting a pragma OpenMP parallel 4 before this for loop. So some of you might not know OpenMP. OpenMP is one of the de facto standards for data parallelism in high-performance computing. This is how you tell the compiler to optimize or to parallelize this loop. And that's simple. And therefore, expression templates are easily parallelized. Okay. Unfortunately, this is a little short-sighted. First, slow code always scales well. If you have a very slow code, yeah, then parallelizing something, of course, doubles, triples, whatever number of processes or cores you have available, the performance, because this overhead of creating threads, of running threads, doesn't count. The amount of work that you have to do is so enormous, so slow, that, well, you can scale perfectly, kind of. But this is, of course, not an argument for easy parallelization. You also, in this particular case, couple a parallelization paradigm to the actual logic of your code. And this is a no-go. This is a true violation of the single responsibility principle. This should, of course, not be done like this. So from a programming point of view, this is just plain wrong. Also, this doesn't distinguish between small vectors and large vectors. Now I'll show you why. So one example from a library, from one of the few libraries that is actually parallel. So most linear algebra libraries, C++ libraries, are not parallel at all. So you might get one or the other function that is parallel, probably in the matrix multiplication, because people realize we have to do something here. But usually these libraries are not parallel. One glorious exception might be the MTL, which is at least, not at least, which is shared distributed memory parallel. So you can scale this across thousands of cores. That's great. But in general, these libraries are single core. So you'll get a tiny bit of maximum performance from these, from the contemporary architectures. Okay, so this is one example of how parallelization could be done. So vector addition, I have 3 vectors. This is the expression. What I have to do is essentially I have to determine the number of tasks somehow, depending on the size, on the kind of data, whatever. And then I just compute subvectors, subvector addition. And this is something that you can package, tasks that you can give to several processors. This is more general. This can be used in an OpenMP, a Boost thread, C++11 thread, Silk, whatever approach. So this, of course, requires a lot more effort. This is not just I write a function, then everything works. This here is, from an architectural point of view, truly complex to do. I don't want to go into detail, though. This is what a parallel vector addition looks like. In this range here, so until approximately 10,000, parallelization doesn't pay off because the parallelization overhead is just too large. So the performance would be somewhere down here. So you need some kind of parallelization threshold. This is something that you have to profile for, that you have to find out. What is the right threshold for your architecture? But then, if you are above this threshold, it really pays off. So you get to completely new heights. And the especially important point is this one here. Only with several threads you can actually break this memory barrier. So the bandwidth of a single thread is bound here. Several threads can actually do more. So the peak performance is considerably higher. A factor of 2, 2.5, a factor of 3 even. Okay. In case of the matrix multiplication, we would expect kind of a perfect scaling. This is exactly what you want to see. So starting from this threshold, we truly want to see that 2 threads are twice as fast as the single threads. 4 threads are 4 times as fast, and so on. So this is what we truly need, parallelization, in order to fully use a contemporary CPU. Question? So this CPU has 10 cores, kind of a special one. So compute centers usually have some special CPUs, a little more expensive, of course. So expression templates are simply not easily parallelized. This attitude completely ignores all the difficulties that go into parallelizing properly. So just adding a pragma is simply not giving you anything, not for real. Okay, last statement. Expression templates are obsolete due to C++11 move semantics. Okay, I truly hope that by now you have understood that it is not about this copy operation and removal of a copy operation, whatever. So I think this statement is simply a statement about the completely wrong view on expression templates. So expression templates, so move, first off, still involves a temporary. You have to create some temporary that is moved. Bad thing. Second, expression templates are not just a remove temporary technology. The big advantage from my personal point of view lies in the lazy evaluation. Lazy evaluation is in fact key to some pretty interesting optimization. So I don't want to truly say optimizations here, but I'm lacking the right term. So let me show you what I mean. Some examples. Assume that we have a symmetric dense matrix. We have a compressed vector, so A and X. We have a dense vector called Y. We just want to compute a matrix vector multiplication. So the dense matrix times the sparse vector, and we assign this to a dense vector. This looks about right. The matrix is row major, meaning, well, row times vector, the data fits perfectly, we should get the maximum performance. So what you cannot know as a mere user of this library is, of course, that the underlying data is still not perfectly suited to truly come up with a maximum performance. Unfortunately, if we would use a column major matrix, we would get a performance about 3 to 4 times faster because the other operation can be vectorized. This operation, unfortunately, cannot. But this is something you as a user cannot know. You would have to truly know the implementation. Expression templates can now help you. They can't just transpose the symmetric matrix. The transpose of a symmetric matrix is still the same. So this operation now uses column major times vector. And this has about 3 to 4 times better performance. Something that happens under the covers, of course, but something that helps you. Okay? Different example. We have 2 dense matrices, A and B, and we have a dense vector, a column vector. So we have 2 X and Y. We again compute matrix vector, but this time we have matrix A times matrix B times the vector, assign this to a vector. So why not? So this is actually a shorthand of something that is truly used. So if you want to rotate a matrix, you have to do matrix times matrix times matrix. So it's just a little easier. Also looks innocent. However, unfortunately, multiplications are validated from left to right, which means that in this case, we first do a matrix-matrix multiplication and use the result to do a matrix vector multiplication. And this is, of course, way more inefficient than if we would just do this first, the matrix vector multiplication, followed by a second matrix vector multiplication. If your library is truly clever, smart, then this restructuring of the expression is possible. Then the library realizes, oh, I can do this much more efficiently, and restructures your expression accordingly. Also, this here, the result of this vector is immediately used in another matrix vector multiplication. It would be much better for performance to introduce another temporary. Otherwise, I cannot efficiently use the values here. So the library might recognize the fact that we need, in order to achieve a high performance, a temporary, fill the temporary with a first matrix vector multiplication, and then use it afterwards. So this is what truly gives you maximum performance. This is something, of course, that you can also do manually. But the library saves you the trouble of truly thinking about all the details. So I don't think this is truly an optimization. And I don't think this is a contradiction to the earlier statements that expression templates do not optimize code. I think this is something different. This is a prevention of inadvertent pessimization. So pessimization is not a real word, but I think you know what I mean. Yeah? You inadvertently, because you don't know the details, use something that is slower than you would expect. And if the library is clever, it might do the according restructuring of expressions. Okay? So, as I said, I think this is simply a wrong statement. Expression templates are much more than just remove a copy operation. So, to sum up, there are a lot of urban legends, as you've seen. Urban legend number 1, expression templates are a performance optimization. Please never ever tell someone, use expression templates, then your performance will go up. This might be exactly the opposite. His performance might go down considerably. Second, please don't tell anyone that expression templates help the compiler to optimize code. The compiler is pretty helpless in this case. The compiler cannot do everything for you. You have to, if you want performance, to profile manually and then to optimize manually. Also, don't believe that expression templates provide an easy way to parallelize. Parallelization is much more complicated, unfortunately. This is exactly the truth that you have to face today. And last but not least, move semantics is, in a way, a replacement of this technology. Okay, the facts on the other side. Remember that C++ does not provide you with performance, but it gives you control over performance. Keep this in mind, please. I think it is important because otherwise this tale of C++ being a slow language is continuing. I don't want that to happen. If performance truly matters, and with linear algebra libraries, it simply does, it's the most important metric, then don't trust your compiler, do profiling instead. And yeah, don't believe expression templates are performance optimization ever again. Which brings us back to the first slide that I showed you. The one to have a linear algebra library in the standard. Currently out there are a couple of libraries that might qualify, but there is a vast number of libraries that truly do not deliver the performance that you would expect from such a library. And I'm pretty much worried that this is not seen, that they're selecting something because it's convenient to use, because it's, well, just nice and has a lot of features. I think this is truly dangerous. If someone selects a library that is just convenient to use without considering performance first, and perhaps only, then this is a truly dire statement for C++ in general. So this is exactly the message that I have. Please don't select because it's nice. Select because it's fast and only fast and delivers maximum performance. Okay, that's it. Thank you.
We still have some time for some questions.
Of course, I expect some interesting questions.
So can you go back to your, let's say, sum up slides with all the
summary slide?
No, the one where everything is, okay. So I have remarks first, two actually. So this is actually a very important topic you touched there, and some of your results there are very important. But I think some of them are actually slightly missing their targets. So first, I think we should actually separate two stuff. Expression templates as a C++ idioms for implementing domain-specific embedded languages. That's what expression templates are for. That's a technique for doing this. And the other stuff is what domain-specific embedded language can bring to a library as a design decisions. So for your two first items, which are green for the user side, are actually should actually read domain-specific embedded language are easy to use and apply. That's
true.
And I can see how we can translate into expression templates because that's the only, let's say, sane way to do DSELs in C++. For the other points, I think that your last points, yes, it means something you actually managed to speak of before. It means benchmarks. We did some tests, okay, on the regular simple A plus B test. And whenever you have a very small, trivial, non-n cube or n square operations, you basically get the same performance using move semantics, because the compiler using move semantics and comp elisions mostly give you something which is close to that. Now, when the expression grows and starts looking like a really huge, complex set of algorithms going on and on, yes, that's true. So it could have been good if you could have a bunch of benchmarks there. It could actually push the point of these items.
But you still agree it is not replacing it?
Yes, it's not replacing.
Exactly the point.
It replaces some instance of it. I mean, if you're just writing an expression templates library for doing like plus minus times and divides on vectors, probably not, that useful. You need to have a full-blown domain-specific driven optimization opportunity, which goes with the 1, 2, 3, 4th stuff. So the question I have is, with respect to all of that, what should be your recommendation about a way to actually design such a library? What should be the main focus on how should you start? Because most of the example you gave, like Eigen and MTL and everything that, all those developments started by, let's make something that looks like, let's say MATLAB or whatever, I mean, a high-level table-based library. And then at some point, and then slap that to get performances. Okay,
but that's exactly how it worked. So in case of Boost, the first thing they did was to make it convenient to use. And they explicitly said that we take care of performance later. They never came to this point. So performance should be the #1 reason to write such a library. So this answers the question, hopefully.
I remember there was a project trying to replace the backend of UPLAS by calls to the MKL. I haven't looked at it,
okay.
But the idea is maybe it's not the point by developing a full linear algebra for the standard, but maybe only a nicely to use front end, and then replace the back end by the library that's fast and specific to the platform you're using.
Okay, I agree. So first point, so there is indeed, so now I have to be cautious. Also in Boost UPLAS, it is actually possible to use the MKL behind the covers, so that a matrix multiplication would also have the same performance as I showed. I've specifically decided not to use that. I do not want to make people believe that everything in Boost UPLAS is also optimized. This is a single point of optimization. A truly single point. If you use something like a dense times sparse matrix, this is so slow you will not be able to finish the benchmarks. So I usually cut the benchmarks because it was truly, well, okay, worst thing that you can get. So true, for dense matrix multiplication, you can also use the MKL. This is already in Boost. And if the standard has just a front end and you have to decide on something fast in the back end, of course, could work. I think what they truly need is just the most important linear algebra operations. And this is just vector addition, matrix vector, matrix multiplication, whatever. If this is, by whatever means, made available such that it can run with maximum performance, great. I'm just worried that they select something because of convenience to use. Because it should be easy to use, of course. And if we do that, this might be devastating.
Okay, thank you. It's after 4 o'clock. Let's have a coffee break. Thank you.
Perfect.